Okay, we're in the second day of our new unit on probability and combinatorics. If you didn't understand the joke on this t-shirt, go back to your notes from yesterday and remind yourself the meaning of a probability of 1 or the meaning of a probability of 0. Probability of 0 has a specific meaning. A probability of 1 has a specific meaning. And if you understand what a probability of 1 means, that's a hilarious shirt. And if you try to do that and you're still not sure, then ask me on the discussion board, on email, and Zoom. We're gonna Zoom today. No, we're not. Today is Friday. Sorry. But you can ask me anytime. I'm Zooming at 1:30 always. You can jump in that Zoom and ask me. Okay, the assignment last night, LO8A.1. I'm gonna go over the answers first. You count the minus number, get that grade to me by the end of the day, please. Don't forget to do that, please. It gets really confusing when these grades don't get reported the day they're due, so do your best to get that done today, please. And after I go through these, if you missed any of them, you should scroll the video to the point you need, and I'm going to go over every single one of them. Okay, number 1 is 2/9. 2 is 7/9. 3 is 7/11, or 7 to 11, or 7 colon 11. I should really have this in front of me, and I don't. Oh yeah, because that one was odds, and so probability or odds could be shown in any one of these three ways, but odds are more typically shown this way or this way. But any form you chose to show them in is fine. Number 4, 1/3. If you have 2/6, I don't think I said to simplify, so 2/6 would be okay too. But we should simplify to simplest form, generally. Number 5 is 4/6 or 2/3. 6 is 1 to 2 or 2 to 4 if you didn't simplify. And any way of showing that with the word 2 or as a ratio, a fraction form would be fine. 7 is also 1 to 2. Going back to 6 for a second, multiples of 10 would be 10 and 20 on that spinner. 10 is a multiple of 10, it's 1/10. The greatest common factor of 10 and 25 would be 5, so it's the same as asking the odds of spinning a 5. Number 8, 3 red, 3 green, and 2 blue. Number 9, there would be 2 cherry chews. Number 10, 3/7. If you have 15 35ths, that's fine. It's just not simplest form, but that's fine. It's a geometric probability. Number 11, 3 to 1. If you have 3 pi over pi, that's fine too, but you see that the pi's would cancel there, so 3 to 1. Number 12 is 30%. If you have 3/10, consider that minus 1/2, because it does ask for the probability to be expressed as a percent. Okay, now if you understand why let's say you missed none, or you missed the ones that you missed, you already understand why you missed them, then you don't have to watch the rest of this video. Nobody has to watch the rest of this video, but go to the parts of the video you need for the problems you missed so you can get the feedback on the assignment. Okay, number 1, I should read the directions first. For problems 1 through 3, assume that a dart is thrown at the square target shown and lands somewhere on the target. So it's going to land within this square on one of these differently colored triangles. What is the probability that the dart will land on a white section of the target? Well, there are 1, 2, 3, 4, 5, 6, 7, 8 favorable outcomes. And I could count all the triangles, but why would I do that? There's 4 triangles in each square, and it's a 3 by 3 array, so there's 9 squares, and 4 times 9 is 36. So there's 36 possible outcomes, or 36 places that the dart could land. 8 and 36 both have a common factor of 4. So if I simplify, I get 2 over 9, which is why the answer is 2/9, 2 to 9. What is the probability that the dart will land on a section of the target that is not white? Well, I should have written this before. This is probability of white, 2/9. Probability of not white must be 7/9, because probability of white plus probability of not white equals 1. And that's getting back to the joke on the t-shirt. A probability of 1 means 100% probability. It's certain to land on white or not white. It's going to land, we've already said it's going to land in the target. It's got to land on a white space or a space that's not white. So those two probabilities added together should add up to one whole. Those are complementary events. And so I just took 9/9 and subtracted the 2/9 to get 7/9. If you took the time to count them up, you would have 28 sections that are not white out of 36, which simplifies to 7/9. The odds of landing a dart on a blue or yellow section of the target. So blue or yellow is a simple event where blue or yellow would be favorable. So odds of blue or yellow, odds shows the ratio of favorable to unfavorable. So if I count the favorable outcomes by counting the blue and yellow, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 if I didn't miscount. 14 favorable outcomes, which, since I have 36 possible outcomes, must mean I have 22 unfavorable outcomes. And 14 over 22, there's a common factor of 2, so that becomes 7 and that becomes 11. So the odds are 7 to 11. If you wrote 14 to 22, just know that you should simplify this the same way you simplify a fraction. Factor out the common factors. But if you didn't know that, 14 to 22 is a good answer. That's fine. Use the fair spinner. This is an important word because that tells you that the spinner is each space. The chances of the spinner landing on any space is equally likely. In other words, the spaces are taking up the same number of degrees. These angles are all congruent for this spinner, and there's no weird rough spot where it's more likely to, if you wanted to make a carnival game and rip people off, you would make it look fair, but you would make some kind of friction, something rough about this section, so it slows down in this section, so it's much less likely to land on a 5. It's least likely to land on a 5 in that case, a little less likely to land on a 25 because it's likely to hit this spot and slow down. All right. I come from a long line of carny folks, so I know all these tricks. What is the probability of spinning a 5? Well, the tricky thing about this is you have to realize there are two, it's an unfortunate choice of color there are two spaces labeled 5, and so there are 2 favorable outcomes out of the 6 possible outcomes, and that's why that simplifies to 1/3. Other than a 5, there's a complement, so 2/3, 3/3, minus 1/3, or you could just count them. There's 4 out of 6. Odds, so whenever we see odds, we have to take a breath and remember that it's not compared to possible, it's compared to unfavorable, favorable to unfavorable. Now first we need to understand what multiples of 10 are. I'm going to list all the multiples of 10. Well, I can't list them all, we'd be here forever. Counting by tens. 0 is a multiple of 10. It's 0 tens. 10 is 1 10. 20 is 2 tens. So when I look at that spinner, there are 2 multiples of 10. The 10 and the 20. So there are 2 favorable outcomes compared to, I almost compared it to 6, but it's odds. Remember, it's odds compared to 4 unfavorable outcomes. And that's why the odds are 1 to 2, 1/2 or 1 to 2. the odds of spinning the GCF of 10 and 25, the greatest common factor. You wouldn't need to do this, but I'm just reminding you of something we learned earlier this year. The prime factorization of 10 is 2 times 5, and the prime factorization of 25 is 5 times 5. And when you look at those in a Venn diagram, there's a common prime factor of 5. And I check this circle, 2 times 5 is 10. I check this circle, 5 times 5 is 25. The greatest common factor is the product of the prime factors in the intersection. It makes sense, common. The common prime factors. If there was more than a 5 in there, we would multiply those together, but there's just a 5, so the GCF is 5. If you had a fraction 10 over 25 and you simplified it, you would factor out the 5/5, right, to get 2 over 5. So 5 is the GCF. So then once you know that, it's the same as saying the odds of, I should really spell the word odds so that's not confused for a 0, the odds of spinning a 5. When there are 2 5s, so 2 favorable outcomes, 4 unfavorable outcomes, the spaces that are not 5. And so that's again 1 to 2. Number 8. There are 8 marbles in a bag. These include red, blue, and green marbles. Red, blue, and green marbles. Anticipating a table. The probability of drawing a red marble is equal to the probability of drawing a green marble. Probability of red equals probability of green. There are more red marbles than blue marbles in the bag. There are more red than blue. Well, if there are more red than blue, the probability of red must be greater than probability of blue. How many marbles of each color are in the bag? This really doesn't have much to do with probability the more I look at it. As long as you understand that if the probability of red equals the probability of green, like let's just go back to the definition of probability. Favorable over possible. So if there's 8 marbles in the bag, the denominator is 8. In order for the probability of drawing a red marble to be equal to the probability of drawing a green marble, there must be the same number of favorable outcomes for red and green. It was just another way of saying there are equal number of red and green marbles in the bag. Given that relationship, I regret my ordering of my table, so let me adjust. I would say I'd probably put red and green next to each other. And we know red and green have to be greater than blue. Since the probability of red is greater than the probability of blue, that means however many red marbles there are, there must be fewer favorable outcomes. In other words, fewer blue marbles. So if red equals green, if you have 1 red and 1 green, you can't have any blue in that case, because for there to be more red and green than blue would have to be 0. So it can't be 1. If there were 2 red and 2 green, in order to have fewer blue marbles but still have some blue marbles, you'd have to have 1 blue marble. But there's 8 marbles, and that only adds up to 5. If you have 3 red and 3 green, that's you could have 2 blue or 1 blue and have a greater probability of red than blue, but it must be 2 because they have to add up to 8. 3 plus 3 plus 2 is 8. And so there's the answer. 3 red, 3 green, 2 blue. Number 9, a bag of fruit chews contains 2 cherry chews, 3 lemon chews, and 1 orange chew. How many cherry chews must be added to the bag so that the probability of choosing a cherry chew is 1/2? Interesting. Let's look at the current probability of cherry chew. It's 2 favorable outcomes over 2, 3, 4, 5, 6 possible outcomes. That's a third. All right, if I'm going to add some unknown number of cherry chews, do you understand if I say 2 plus C? 2 plus some additional number of cherry chews would give me more favorable outcomes. And that my total possible outcomes, the total number of chews in the bag, would also be 6 plus C, because I'm only adding cherry chews. We want that to equal 1/2. So I want you to see that this can be solved algebraically using cross products, because we've done this. The cross product would be 2 times 2 plus C. This other cross product would be 1 times 6 plus C. Now when I said we've done this, I don't mean we've necessarily used cross products algebraically. It came up in class a couple times, but it certainly wasn't a focus. But I just want you to understand that we did cross products, and you can apply them to an algebraic proportion. You have applied them to algebraic proportions, just not this specific type, but you can. If I distribute this 2 to both terms, 2 times 2 is 4, and 2 times C is 2C. There's no need to distribute this 1 to both terms, because 1 times 6 is 6, and 1 times C is 1C, which is C, so I just have 6 plus C here. If I subtract C from both sides, I get 4 plus 2C minus C is 1C. So 4 plus C equals, the reason I subtracted C is to make the C go away here, so I'm just left with 6. So if 4 plus C is 6, C must be equal 2. So you can add 2 cherry chews to get a probability of 1/2. This is not the way I would expect you to solve this problem. I just wanted to, especially if you're taking the time to use this part of the video, I want you to see that you can do it algebraically. What I would expect you to do is, if I add 1 cherry chew, what am I looking at? I'm looking at a new probability of 3/7. That's not 1/2. If I add 2 cherry chews, I'm looking at a probability of 4/8. There's 1/2. Guess and check's a lot faster in this case, but when problems get more complicated, and they will very soon, you want to know that there's an algebraic approach. The algebraic approach will be more efficient if the numbers are less friendly and the situation calls for it. Number 10, if a raindrop lands on the figure shown, what is the probability that it will not land on the shaded region? Probability of not shaded is the same as saying the probability of the white region. So the white rectangle has an area of 15 centimeters squared. For probability, I want to compare favorable to total. So I don't need to do any subtraction, any composite area. I just need to think about the whole big rectangle is a 7 by 5, so 35. The area was 35 for the whole big rectangle, including the white rectangle. So the area of the whole is 35. The white area is 15. So the probability of white is 15 over 35, and those have a common factor of 5. So 3 over 7, 3/7. Let me double check and make sure I didn't give you any wrong answers. Nope, not yet. Okay, number 11. If a raindrop lands on the figure shown, what are the odds that it will land on the shaded region? Now, careful, odds, not probability. Odds, shaded, will be the favorable outcomes, which is the same as the area that's shaded, compared to the unfavorable outcomes, which will be the area that's not shaded or white. The shaded area, okay, let's do the area of the whole circle would be pi r squared, and the radius of the whole circle is, if this is 1, well, actually I don't even need that, do I? For the whole circle, they give us the radius directly down here. They're showing us that this whole thing is 2. So if that's 1, this must be 1 also, right? Right, so r is 2. We're squaring that. And I want the exact odds. I don't really need to be changing pi to any estimate. It's not called for in a situation like this. So the area of the whole circle is pi times 2 squared, or 4 pi. The area of the whole circle. The area of the white circle, also pi r squared, but then the radius is 1. Pi times 1 squared, that's 1 pi, or just pi. The area that's shaded is the whole circle minus the white circle. 4 pi minus 1 pi is 3 pi. So the area that's shaded is 3 pi. The area that's not shaded, the white area, is 1 pi. And pi divided by pi is 1. And so it's just 3 to 1. If you say 3 pi to 1 pi, I understand it, and that's fine. Or 3 pi to pi. Just know that pi divided by pi is the same as, it's like factoring out any other common factor. Refer to the data on the world's tallest buildings below. Tons of data. That's intentional. Suppose the names of the 10 tallest buildings are put into a hat and one name is drawn randomly. Express as a percent. This is not worded well. I wonder if I reworded this, and it should say expressed as a percent. No. Oh no, it's worded fine. Expressed as a percent. What is the probability that the building drawn is 100 or more stories tall? The reason I said there's a ton of data here on purpose is because sometimes with problems like this, you have more data than you need, and part of the exercise is understanding what data you need. We're calculating the probability that the building drawn is 100 or more stories tall, and so I've got stories here. I've got height in feet, I've got height in meters, I've got the year the building was completed, when it was. None of this matters. We're just concerned about which ones are 100 or more stories tall. And it doesn't tell you how many buildings, it just says the world's tallest buildings. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 buildings. So 10 possible buildings to pick from the hat. Remember, we're putting them all in a hat and picking one fairly. That's the possible outcomes. The favorable outcomes would be the ones that are 100 or more. So this one, and this one. So 3 out of 10. Expressed as a percent. Percent is out of 100. 30 out of 100, so 30%.